In today's video, I am going to go through together problems related to working on ice tables, and I'm going to focus on number 47 and number 48b, okay, is what I'm going to work on today. So 47, it gives us at 22 degrees Celsius, Kp is 0.050 for the reaction. Now, again, the only reason they're telling us the temperature is that K's are temperature dependent. It wants to know the partial pressure of nitrogen dioxide in equilibrium with N2 and O2 that were placed in a flask at initial pressures of 0.80 and 0.20 atm respectively. Okay, so if I come down here, let's get back to this one here. I have, first of all, one of the things that we're going to be focusing on today, and the reason that these are together problems, is that this is going to be ice tables with either the quadratic formula or just a little bit of funky math. Now, if it's been a while since you've done the quadratic formula, here is the basic format for it. And also, if you look in your Zumdahl textbook, in Appendix 8 1.4, page A8, you can find it. Also, if you go to Khan Academy and you Google quadratic formula, search quadratic formula, it will show up there as well. So not easy math, which is why this is one of our together problems. Okay, so for 47, I've already set up the ice table here. As a reminder, evidence that you've watched this, you need to write this down. So if you need to, go ahead and pause this, jot it down, because this will be part of what I'm checking off for your homework next time. Okay, you've got nitrogen plus oxygen gives me 2 NOs. And our Kp value again is 0.050. I've got my initial concentrations, my changes. Remember, since they give me reactants, these are going to be negative x and negative x plus 2x. And then I have my equilibrium down here. So I set Kp up to the equilibrium expression, and I went ahead and plugged it in here just a little bit. You've got 2x squared, because that's a 2 in front of it. Don't show me this message. I've got 0.80 minus x and 0.20 minus x. Now, the reason I can't just scribble out the minuses here is that my initial values and my KPs are too close. Okay, remember, the only time that you can kind of cheat a little bit is when the values are off by at least 3 decimal places, and they're not here. So that's part of the reason that we need to be able to keep it. Okay, and again, if that doesn't make sense, please ask, but it's 0.050 is not 3 decimal places off, so it's not going to change this. It's going to change the significant figures enough that we can't just plug and chug. Okay, so I've got this set up here. If I go ahead and reduce this down just to kind of show you some of the math, the next step on this side would be, if I distribute this stuff on the bottom, what I end up getting, I've got 0.050. I'm going to end up with 4x squared over 0.16 minus 1x plus x squared. Okay, that's what would be on the bottom. And so obviously my next step in manipulating this would be to take 0.050 and multiply all of these things out. So if I multiply both sides by this right here, what I end up with is going to be 8.0 times 10 to the negative third minus 0.050x plus 0.050 x squared, and that's going to be equal to 4x squared. Okay, so then if I go ahead and bring the 4x squared over, what I'm going to end up with, actually what I'm going to do is bring everything over to the 4x squared side. So I'm going to take this stuff and subtract and end up with it over here. So I'm going to have 0 is equal to 4x squared. Nope, I'm lying. Let me change that here. Do my math correctly. If I take 4 and subtract 0.050, I'm going to end up with 3.95 x squared plus 0.050 x minus 8.0 times 10 to the negative third equals 0. Okay, then what I have to do is go ahead and use the quadratic formula. Now, I'm not going to show you how to solve the entire thing. Some of you are great at it, some of you not so much, but I take these numbers and I put, and not necessarily not so much, but you need more practice at it. So because we're in different phases and different places, I'm just going to show you how to set it up, and then you need to work out, manipulate it, make sure that you can get it done by yourself. So if I plug everything in, I've got negative 0.050 plus or minus. Remember, we're going to have the square root of everything under here. 0.050 squared minus 4 times 3.95. I realize I need to extend my square root here. Negative 8.0 times 10 to the negative third. We've got all that to the square root, or to the all of that raised to the 1/2 power, however you want to look at it, over 2 times 3.95. Okay, so again, take the time to solve this, particularly if it's been a long time since you've done the quadratic formula, just to make sure that you can work it out. Now your x values here are going to end up to be 3.9 times 10 to the negative second ATM, or negative 5.2 excuse me, times 10 to the negative second. Now you can't have x be negative, so we're going to lose that one right away. So x has to be 3.9 times 10 to the negative second. Now why the heck were we doing this in the beginning? Well, what we were trying to solve for is what is the partial pressure of NO. So if we go back to our equilibrium expression up here, remember NO has to be 2 times x. That's how we're going to figure out what it is at equilibrium, because whenever we find x we have to go back to the ice table and actually solve for the values. So my partial pressure of NO is going to be 2 times 3.9 times 10 to the negative second, which is equal to 7.8 times 10 to the negative second ATM. So the only reason this ice table is any different and is really ugly is got to do this quadratic formula, but the mechanism is still exactly the same of how you need to solve it. Okay? So that is 47, and obviously, you know, getting to this on a test or a quiz, you know, if you show me the ice table, show me the KP set up, let's say you totally tank on the algebra and you can't figure it out and you're not sure what the quadratic formula is, we'll make up an x value. Remember, it would be totally acceptable to then say, if x is equal to this, show me you know how to solve for the nitrogen monoxide down here. Then you only lose points for not the quadratic formula, but you show us most of the problem. Okay? Alright, now the next one that we're going to set up is going to be 48b. You have it 25 degrees Celsius, capital K. Now remember, this is going to be concentration. Sometimes you'll see it as K lowercase c is equal to, you've got water reacting with our chlorine and oxygen compound. So, and they're all gases, so they're all going to count. None of them are heterogeneous. But it says calculate the concentration of all species at equilibrium for each of the following cases. You have 1 gram of water and 2 grams of the Cl2O are mixed in a 1.0 liter flask. We're not doing that one, we're doing letter B. 1.0 mole of our product is placed in a 2.0 liter flask. Okay, so what are we trying to solve for? We're trying to solve for the concentration of all of them at equilibrium. So again, step is always going to be to write the balanced equation. They give us the K value, so it potentially could be Kc here. Okay, you'll see me write it both ways. I've got the equation, I've got my ice table. Now, one of the things that is a little curveballish here is the data they gave us in the beginning. Remember, it was 1 mole in 2 liters. And since we want concentration, we need to take 1 divided by 2 and get 0.50 liters for our initial here. Now the other reason this is a little quirky is that we're actually going to look at it going in reverse. So because these are reactions that can go in either direction, even though this is written as our product, we're looking at it in reverse. So therefore, when we look at our signs in the ice table, we have negative 2x as the change here, positive 2x, or sorry, positive x and positive x. And we're solving for the equilibrium expressions for all of these. Okay, so let me get back to my pen here. Again, I have my equilibrium expression. You can write the C, you don't have to. It's 0.90. And then we go ahead and we plug and chug. So if we look at on these, we're going to have 0.0, no, sorry. Dun, dun, dun. Heaven forbid I not make a mistake on this stuff. Where did we go? I lost it. There we go. 0.50 minus 2 x squared over x squared. Alright, now you might be looking at this going, oh man, this isn't small enough, we can't subtract it. Well, that's just ugly. Well, yeah, so we could do the quadratic formula. If you want the quadratic formula, go ahead and do quadratic formula. So you may be thinking you have to do the quadratic formula, and you don't, because here's why. If you look over here, these are both squared. Okay, so what we can do, remember, if we do one thing to one side of the equation, we can do the same thing to both. So since the expression is a perfect square, we can just take the square root of each side. So let me do a different color here just to show you. So I'm going to go ahead and take the square root over here. Remember, the whole thing is equal to 0.090. Take the square root of there, and that's going to knock those right out of the way, which just is a lot easier unless you love the quadratic formula and you want to spend all kinds of your time doing it. Great. I don't fall into that camp. Okay, 0.0, no. Whoa. Okay, 0.30. It's going to be our answer over here. We've got 0.50 minus 2x over x. Okay, a lot easier to manipulate this one. So what we end up with, 0.50 minus 2x equals 0.30x. If I bring the 2x over to the other side, I've got 0.50 equal to 2.30x. Dun dun dun. So x is going to be equal to 0.217. Yes, I went ahead and carried an extra significant figure here because I got to plug it back into my ICE table. Now I do only need 2 sig figs in my final answer. So because we're dealing with concentration, the concentration of the water, both reactants were both 1s. So they are flat out just going to be 0.22 molar. Don't forget the molarity units here on this stuff. And then for our product, we just plug it back into the equilibrium expression, right there. That's going to be 0.50 minus 2x. So if we plug that back in, 217, what we should end up with 0.070 molar. Okay? All right, there you go. I hope that helps. We'll keep asking questions.